This lab explores the most basic representation of the physics of extreme sports with ropes using a simplified spring mass system. In the video provided, a mass swings in an arc while oscillating on a spring. The goal of this lab was to use the tracker and VPython software to create a model representing this motion. The first step was to load the video into Tracker and track the point mass through each frame. Here's my tracker video. Then I created a code in VPython to recreate the motion. I imported the X and Y position points from Tracker into a CSV file and input that into Python. Finally, I ran the code and compared the predicted motion from the code with the actual motion from the CSV file data points. In the end, I found that the predicted motion and the observed motion were very similar. The graph produced in Python showed very little divergence between the points of the two data sets. I also observed the energy through graphs produced by my Python code. According to the graph, the energy principle is satisfied as the sum of the energies equals 0. There were various initial conditions that were necessary for the completion of this lab. First, the length of the spring was given as 0.7 meters. The origin, used for calibration and Tracker, was the point of attachment of the spring. The mass was 0.402 kilograms. From the Tracker video, I then obtained the initial position to be negative 0.125, negative 0.660 meters. The mass also starts at rest, or in static equilibrium, so the initial velocity of the ball was 0. The next value I calculated was the spring constant, Ks. In order to calculate Ks, I first calculated the period, t. This came from the video. I took the average of 3 oscillations of the mass spring system, and I obtained a time of 1.614 seconds. Then I plugged this value into the equation for period, and I solved for the variable Ks. I obtained a value of 6.83 newtons per meter for my spring stiffness constant. Next, I calculated the value of L0. This calculation used Newton's second law. First, I summated the forces on the system. Since the system is at rest, the force of the spring plus the force of gravity equals 0. I set the magnitudes of each equal to each other. I then incorporated Hooke's law, which says that the force of the spring equals K, the spring stiffness constant, times S, the displacement of the spring. I solved for L0 and I obtained a value of 0.14 meters. Now let's take a look at my code in VPython. I first input the mass of the ball's initial position, and the ball's initial velocity. I also set the gravitational force near Earth's surface to 9.8 meters per second squared. I set the value of Ks to 6.83 and L0 to 0.14 as calculated previously. I put in the length of the spring and calculated S, the stretch or compression of the spring. The next step is to set the value of the kinetic energy, gravitational potential energy, and the spring potential energy. Then I implemented Newton's second law when summating the forces and updating the ball's velocity and position. The next step was to update the spring's position and force for each iteration. The final step was to calculate the energy changes. I calculated delta K, delta U sub G, and delta U sub S. Based on the energy principle, delta E is 0. Therefore, when I added the kinetic energy, the gravitational potential energy, and the spring potential energy, I set the value equal to 0. This is the result when I run the program. In the graph of the position versus time, the red curve represents the values input into the code through the CSV file. This is the observed position data. The blue curve represents the actual prediction calculated by the code. The two curves are very similar. The variations between the two are due to human error in the tracker phase of the lab. Now let's examine the graph of the change in energy versus time. The green curve shows the spring potential energy, the red curve shows the gravitational potential energy, the blue curve shows the kinetic energy, and the yellow curve shows the total energy. The spring and gravitational potential energies are equal in magnitude but opposite in sign, due to the movement of the spring. The weight force always points down and the spring force always points up because the spring is always longer than its natural length during the entire course of motion. However, the mass gains and loses kinetic energy, hence why the graph shows the curve oscillating between positive and negative values. The kinetic energy changes approximately twice as fast as the potential energy changes. For my model system, the energy principle is satisfied. The plot shows the net energy change as 0, which reflects the energy principle. The system is closed, so there are no external forces acting on the system. Also, the system is separate from its surroundings, which is necessary to calculate the potential energy. Using the data I obtained in Tracker, I calculated the period of oscillation from the X data to be 1.614 seconds, and I calculated the period of oscillation from the Y data to be 1.551 seconds. The vertical and horizontal periods don't have to be the same. The vertical period depends on the spring constant, and the horizontal period depends on the force of gravity. However, in this case, the x and y periods are very close to each other.